Hello everyone and welcome to the Big Bang. You may be wondering, why do we need to think about and clearly state our assumptions when solving all these mass transfer problems? As you may have realized by now, real systems are too complicated to model completely using mathematical equations. Assumptions help simplify the system so that we can try to predict certain phenomena using known principles of mass transfer. In this video, we will go over some of the most common assumptions you will make for solving mass transfer problems. We usually assume isothermal and isobaric conditions in a binary dilute solution. That means that density and diffusivity remain constant, and Fick's first law applies. In the beginning of the course, you assume no convection or bulk fluid motion. Next, determine the direction of flux, which is most likely one-dimensional. Are the coordinates rectilinear or spherical? Is flux in the positive x direction or inward or outward radio? A great way to assess what assumptions you need are to refer to the material balance. After reading the problem statement, what problems in the material balance can you cross out? You will rarely have a problem that includes all terms in the material balance. Let's briefly go through each of these terms, which we simplified and wrote as A equals I minus O plus P minus C. First, let's look at the accumulation term, or A. At steady state, you can cross this term out. If there is a constant source and sink, then you are at steady state. If instead the mass transfer has time dependence, such as a change in the diffusion path over time, then you are at unsteady state. At unsteady state, you will become familiar with two different assumptions, the semi-infinite or infinite assumption. More details on those will come later in the course. Now let's analyze the in minus out terms, or the I minus O. When you draw a control volume around a schematic, is there anything entering or exiting? Those become your in and out terms, which are also referred to as net flux. For most of the course, these terms pertain to diffusion in or out of the system based on Fick's first law. Whenever you use Fick's first law, remember that you are dealing with a dilute binary solution in isothermal and isobaric conditions. Then, the diffusive flux is proportional to the concentration gradient that serves as the driving force. Some other assumptions that accompany Fick's first law are constant total concentration, constant diffusivity, DAB, and an incompressible fluid, that is, constant density. In addition, if you have a solid or stationary liquid, then you can assume there is no bulk fluid motion or convection. Also, the direction of flux can most likely be simplified to one dimension, either the x, y, or z direction in the case of rectangular coordinates, or inward or outward radio in the case of spherical coordinates. If you are in cylindrical coordinates, you can be in the z direction or in the inward or outward radial direction. To determine the direction of flux, note the source and sink in the system, as well as any symmetry you can possibly find. Finally, let's analyze the produced minus consumed terms. Those were the P minus C. These two terms refer to homogeneous reactions. An easy way to assess if you have a homogeneous reaction is to look at the units. Homogeneous reactions are volumetric. They occur throughout the solution and will have units similar to, for instance, moles over centimeter cubed times seconds, or molar over liters cubed times time. Heterogeneous reactions occur at a surface and will have units similar to moles over centimeter squared times second, or molar over liter squared times time. Note that these are the same units of flux and usually serve as boundary conditions if they are given in the problem statement. In summary, when making assumptions, there are 5 main components in the problem to consider. First, steady state or unsteady state, which affects the accumulation term. Second, solution properties, such as being binary and dilute, that enable the use of Fick's first law. Third, bulk fluid motion or no convection. Fourth, the direction of flux. What is it? Now, number 2, 3, and 4 all help simplify the in minus out terms in the mass balance. But then there's a fifth, homogeneous reactions, which affect the production and consumption terms. Hopefully this video helps categorize the different assumptions you can make so that the problems becomes much easier to solve. Thanks for watching, and I'll see you in the next video.